So as Ariel mentioned, a key component of GIEs is a quasi-experimental method of causal identification. And so one such method that we use a lot is differences and differences. So difference and differences allows us to construct a counterfactual for the treatment group using the time trends of the control group. So if you look at the graph, the blue line represents the control group and the green line represents the treatment group. And the red vertical line represents the time of treatment. So as you can see for the treatment group, after treatment occurs, there's a jump in the outcome variable. However, we know that in the absence of treatment, the outcome variable still would have gone up in time due to the time trend. So in order to know how much of that jump is caused by a treatment, we need a counterfactual to understand how the outcome would have evolved in the absence of treatment. So this is where we use the control group. Since the control group is unaffected by the treatment, we can use the time trend of the control group to estimate what would have happened in the treatment group in the absence of treatment, or our counterfactual. So therefore, the difference between the control and the treatment group and the difference in outcomes over time ends up being our treatment effect. But however, there's a key assumption that underlies this method, and that is that the treatment and control groups must have parallel trends in the outcome variable in the absence of treatment. So moving on, to execute a kind of canonical difference in difference, you need an intervention that was implemented only at one time. You also need a clearly defined treatment and control group. In terms of data, you need observations that occur both before and after the treatment time. And your data can be either a repeated cross-section or panel data, as long as it has these elements. So to calculate the treatment effect, essentially, you'll take two differences, as you'll see on the next slide. The first is the difference between the control and treatment group. And the second is the difference in the outcomes over time. And then the difference in these differences is the treatment effect. So in terms of an OLS regression, what this means is that with the first term after, you end up accounting for the time trends for the treatment group variable. This ends up accounting for differences between underlying differences between the treatment and control group that are just there. And then the interaction of these two ends up kind of accounting for any other differences that resulted because of treatment. So then beta 3 would be our treatment effect that we would estimate. So we put together some code on this that you receive after the workshop that will kind of let you play around with putting your own data in. And the way it's set up, you'll put your own data in, specify the variables, and then the code will run and produce some outputs. So there's two outputs, but the first one is this, which is a table showing the outcomes of the regression. Again, the first two terms, the after and the treatment group, are not the treatment effect. They're just requirements of running the regression. The third, which is the treatment group times after, or interaction effect, the coefficient on that is the estimated treatment effect. We'll also produce a graph from the do file, and it will look something like this. That just helps you visualize the treatment effect, the magnitude, and whether or not it's significant. So again, all this code is designed to set up this data, and we'll provide it afterwards so that you can try it out yourselves. So as we mentioned before, we can only use a difference in differences approach if the parallel trends assumption holds. So the way that we usually test this is using a pre-trends analysis. And this considers whether there was a parallel time trend between the two groups prior to treatment. Of course, we're trying to figure out whether that parallel trend would continue after treatment, but we don't know that because that's not the world we live in. So instead, we look at the pre-trends that happened before treatment. And if they are parallel, then we assume they would have remained parallel after treatment in the absence of treatment. So again, we put together some code for you that kind of runs a pre-trend analysis. And there are two ways to consider the pre-trends. The first is looking just at the raw pre-trends. So this is just plotting the outcome variable against time. And this allows you to see the general pattern. And I think we have an example of that on the next slide, maybe. So this is, again, just very raw, doesn't control for any control variables or fixed effects, but lets you just generally see what was happening beforehand. So in this example, for instance, the parallel trends assumption does not hold, so we'd be a little bit worried. And then the next way that the code looks at this is by actually taking your control variables and the fixed effects and applying them to get a kind of more robust understanding of the parallel trends assumption. So we'll output two different pre-trends graphs that you can look at. And again, we'll share this code after the training. So using difference in difference for a single treatment period is great, but not all interventions, of course, have only one treatment time. Lots of the time, what we run into is that our treatments actually have multiple staggered treatment times or rollout design. So in these cases, there is a generalized form of difference in difference that can be used. And variation in the treatment group, variation in treatment derives from only the treatment group because there's no true control group needed in this approach. So this can also be a benefit if you don't have a pure control group that you've identified. So there's a little bit of a difference in the identifying assumption, whereas before we were only concerned about the spatial allocation of treatment not being correlated with the changes in outcome. Now we're worried about something more. We're worried about the spatio-temporal allocation of treatment not being correlated with the changes in outcome. So it's a little bit more strenuous, but again, you have a little bit more flexibility not needing a true control group. So essentially what this does is it statistically aligns over time the treatment time in the statistical model, and therefore it allows you to estimate the treatment effect based on this, as you can see in this graphic. The way this is done with an OLS is because the time and geospatial fixed effects subsume those kind of after and treatment group binary variables that we had before, we instead just have one binary variable, which we'll refer to as treated for now. And this is a 1 if the observation has been treated by the time it's observed, and it's a 0 otherwise. And so this can change over time, of course, for an observation. So at some points it can be in the control group, and some points it can be in the treatment group. And then the coefficient on this beta is our estimated treatment effect. So again, we have put together some code for you to use that runs a difference in difference regression with the multiple treatment times. The output of this is a table that just has one variable. It's much easier to interpret. And this is the treatment effect. So essentially, over a long period of time, people started to scrutinize this method of difference in differences for multiple time periods with the two-way fixed effect. And the reason being is that it has a lot of underlying comparisons that we don't typically think about that are contributing to the way that the treatment effect is estimated. So the comparison that we want is already treated units versus not treated units. But when this treatment time staggered and you use the two-way fixed effect model, oftentimes a lot of other comparisons are getting grouped into what constitutes a treatment effect, and this can be problematic. So this will be especially problematic if the treatment effect varies over time. So think if the treatment effect grows or shrinks over time. And this is a circumstance that's actually very common in agriculture environmental projects where impacts build over time as people and markets respond to interventions. So this might be something that you run into a lot with your work just by the nature of the interventions. So we'll give a quick illustration of this problem that we're thinking about. In this graphic, we have kind of three groups. The solid line at the bottom is kind of our control group that, as we mentioned before, you don't need, but in this example, we'll include it. And these are people who are never treated in our time period. The triangle represents people that are treated at the first period of treatment, the first red line. And then the circles represent the people who are treated later. So our later treated group. So underlying kind of when we do a different diff with 2 fixed effects in this, we end up with 4 comparisons that we'll show on the next slide. So the top left is the early treated group versus the untreated group. Now, this is a really unproblematic comparison. This is kind of the canonical single period difference we're thinking of. The top right is the late group versus the untreated group. And again, this is unproblematic. It's like the single time treatment difference. The bottom left, we're comparing the early treated versus the late treatment group at kind of before the second period of treatment, so early on. And again, this is problematic again, because the later treated group at this point is just kind of as if they're controlled because they haven't yet been treated. So where we run into problems is the bottom right, where we're comparing the early treated group versus the late treated group after the later treatment period. And to see why this is a problem, we'll show you the next slide. So if the shift is parallel in the outcome, then it might be okay, but oftentimes what happens is when there's a treatment, the outcome variable will jump, and then also perhaps the trend will now shift a little bit. So at the first time, we'll estimate one treatment effect, and then afterwards, we'll be comparing the jump of the later treated to the jump in the earlier treated, and it actually underestimates the treatment effect because the slope changed. So as you can see, kind of this estimate then might get attenuated because of this problem. And this is because the treatment effects can vary over time. So moving on, we have a lot of new literature that tries to fix this problem. And there's a lot of really great papers that have come out in the last couple of years that offer different solutions to this. So we've listed a few, but it's not exhaustive. So Goodman-Bacon tries to address this problem by decomposing the sample across the windows. And this allows us to see how much variation comes from each comparison that we just talked about. So let's essentially understand where the variation is coming from. Callaway and St. Anna use only the not yet treated group as comparisons. Sun and Abram alternatively use the last to be treated as the comparison group. Borjak, Jaraval, and Spice create an imputation estimator that attempts to predict the counterfactuals from the trends among the not yet treated, and then uses these counterfactuals to estimate the treatment effect. And de Chase-Martin and de Heffalier use only not yet treated as comparisons, but they also allow the treatment to turn on and off, which might be useful if an intervention kind of comes, goes, and maybe comes back. But again, this isn't an exhaustive list. There are many others as well.